Okay, now consider the buffer capacity. As I said, mhm, although the giving the same pH, but if you use more compound, yeah, to prepare the same pH, and then um, the gain is buffer capacity. Buffer capacity increases. Okay, or if you use a small amount of the buffer component, and then although you get the same pH, but the buffer capacity may be low, and when strong acid or bases are added, and the solution pH will change a lot. Okay, but with high buffer capacity solution, the pH of solution doesn't change much. Okay, so that's the merit. Okay, but let's define how quantitatively, we define the buffer capacity. Yeah? Buffer capacity is the measure of how well a solution resists changes in pH when strong base or strong acid is added. Okay, this is definition. Okay, beta buffer capacity is denoted as beta equals dCb over dpH. Okay, D means it's a differentiation. In other words, it's a change. Okay, and Cb is what? This the concentration of strong base. And so yeah, this is a definition. So high buffer capacity means what? To change a unit pH, you need the high concentration of strong base. Okay, or it can be expressed by acid concentration. Okay, the pH change is just the opposite when you add a strong acid, and then it is defined by minus here dCA over dpH. Okay, yeah. Here this figure shows how we obtain the buffer capacity. And look at the above the figure. And this one, let's say x-axis is pH, y-axis is what? The Cb, strong base concentration. Okay, you see, this curve is just opposite. Yeah? Usually people, use the y-axis is pH and x-axis is concentration, but this is opposite. Yeah, because to show this buffer capacity. Okay, and you get this curve. All right. Yeah, and uh, if you differentiate this Cb, this concentration change with respect to pH, a simple differentiation of this curve, yeah, and here it increases, and at this point the change is maximum, and decrease. Okay, decrease and almost zero in this region, and then it increases rapidly again. Okay, so what is the maximum buffer capacity here? All right, you see here, yeah, and it decreases, and in this region, yeah, the buffer capacity is minimum. This is not buffer at all, actually, and then at very high, yeah, pH, yeah, buffer capacity also increases. All right, yeah. So this one, this curve actually is the titration curve of weak acid. Okay, with pKa equals 5. Okay, now you turn this curve by 90 degree. Okay, and then you see a titration curve of weak acid of pH of HA, yeah, with strong base. All right, and here at this position, this point is where the maximum buffer capacity is attained. All right, Yeah. But here at this point, what's the ratio of HA and A minus? Yeah. Not this one. At this point, the pH is 5. Okay, and here pKa is 5. So now we can conclude that when pH equals pKa, that point is the maximum buffer capacity point. Okay, here this is very important. Yeah, this is quite understandable because from Henderson-Hasselbalch equation, you see, I will show you again. Go back, go back, go back, go back. Yeah, here, right? In order for pKa and pH to be equal, and this one, the concentration of anion form and HA form must be the same. Okay, from the Henderson-Hasselbalch equation. Okay, yeah. Yeah, this is the, in other words, this is the equivalence point. I'm sorry, yeah, this is the when the equal concentration of HA and A minus forms are there. All right. Yeah. So don't forget that maximum capacity reaches when pH equals pKa. All right. Yeah. And in the practically, good buffer is pH is controlled between pKa plus minus 1. All right. Here in this case, 5 plus minus 1 is 4 to 6. In this region, here in this region, is the actually a good buffer works. Okay, because the maximum buffer pH buffer capacity is obtained at pH 5. Yeah, right. Yeah, that's the empirical result. Okay, and the table 8 2 lists a lot of different buffer components. Okay, so depending on all these components, yeah, they have pKa values. Okay, and so you have many choices. You have to prepare a specific buffer as a specific pH. Okay, so you can take anyone, yeah, anyone, depending on which pH you want, yeah, and then you can pick up the this compound, yeah, and but there are very the common purpose, right, for the biological experiment. Purpose are usually made of trees. Okay, for other purposes you can use other the chemicals. All right, yeah, the table is long. Okay, okay, I will just skip. Okay, and this one, buffer pH depends on ionic strength and temperature. All right, and first of all, you can what calculate how much compound to take. Yeah, but actual calculation, mm, you calculate. Oh, now this amount of compound may give the pH. Okay, mm, but actual pH may be different. Okay, why? Because buffer pH depends on ionic strength and temperature. Okay, here is the example. This is borate buffer. Okay, it works. Its pH is 8.98 at ionic strength of 0.1, but at the low ionic strength, yeah, pH is 9.24. It increases, and the difference is not small. Okay, and for example, this one, this borate, the pKa is 9.24. Okay, but at the high ion strength, pH becomes lower. Yeah? And truth buffer also the pH changes with respect to um, the temperature. At 4 degrees C, the pH is 8.7, but at the higher temperature pH decreases, okay, to 8.07, and at 37 degrees C it's even further decreases to 7.7. Okay, yeah, okay, this is end of this lecture, and I will continue the lecture about the buffer. Okay.